Hello, this is Mr. Doro. Today we're going to be talking about calculating percent yield. This is a continuation of stoichiometry, and if you have a good idea about stoichiometry and mass-to-mass stoichiometry, you'll be doing just fine with percent yield. Today's objective is that you're going to determine the actual yield of products and compare the theoretical yield and determine the percent yield. Now don't let this percent scare you up here. You guys deal with percentage all the time. In fact, if you were in baseball and you were on base or got a hit 5 out of every 10 times at bat, then that would be a batting average of, they call it 500, which is just 50% of the time that you're on base, and that is a percentage, 5 out of every 10 times. Or you could think about percentage of your test score. Maybe you got 78 out of 94, and so you had, your score was 78 points. There were 94 possible, so we put the possible on the bottom, and then we multiply it by 100 in order to get the percentage, and we end up finding out that you got a right around 83%, so not bad. So we're going to put that in here, times 100, and then we got around 83%. So you must have studied someone, or at least paid attention, and so you did a pretty good job. That's what percentage is when we're calculating percent yield too. It's just finding the percent. This is the formula for calculating percent yield, and so you want to write this down. Percent yield is something called actual yield over theoretical yield times 100. That times 100 just puts it in a percentage for us. You can see that percent yield is not going to have any units. It's just going to be percent, because the actual and the theoretical would cancel each other out. So I want to identify what actual is, where you get that from, and where you get the theoretical from. So I'm going to draw some notes on here too. This actual yield right here, this is found, I'm going to write actual. This is found in the lab. This is what you actually made in the laboratory. You actually measured, you came out with, that's how much you ended up with at the end. And then the theoretical right here, so theoretical is what you're going to calculate from an action line. This is what you've been doing before when we did stoichiometry. Everything that you were doing was theoretical. You were saying we should get this amount, we should get this amount if everything went exactly correct. Usually though, your actual yield is going to be less than your theoretical yield. There are times when it could be more than your theoretical yield if you had some contamination in there, or maybe you didn't dry everything out correctly. But we want to find the percent yield. Of course, if we're doing very well, then our percent yield is going to be as close to the theoretical yield. The actual yield is going to be as close to the theoretical as we possibly can. But sometimes it just can't happen that way. Here's a practice problem that involves percent yield. Now the problem is you have to look at the question and see what it's asking for. It is asking for percent yield of water. That's the first thing it's asking for. It gives you some other information that's kind of helpful in here too. It says 30 grams of sulfuric acid reacts with excess aluminum hydroxide. Now we know what that excess means. That excess means that it is not the limiting reactant, it is the excess reactant, or the reactant in excess. So this one right here, the 30 grams of sulfuric acid, is the one that determines how much product you're going to make. So this is your limiting reactant. That's what we're going to want to start our action line with. But also notice this. This gives us a different term in here also. It says it produces 10.6 grams of water in the lab. This is very important right here, the in the lab part, because this tells us that this is our actual yield. The 10.6 grams is what we actually walked out of the lab with, or we actually produced in the lab. So our first step is we need to write a balanced equation. Now you can write a balanced equation, or you can close your eyes and think real hard that you would like a balanced equation right now. Okay, that worked. So here's our balanced equation, and notice that we start out with 30 grams of this sulfuric acid. What we want to go to in our action line is we want to get to water, because it wants to know the percent yield of water. So we need to know the theoretical yield of water. We already have the actual yield of water. In fact, I would label this right in there as the actual yield. So AY maybe. maybe, and circle that. That's our actual yield. I kind of covered up the 1, but that was 10.6. So now what we're going to do is we're going to do an action line, and we're going to go over from starting with our 30.0 grams of H2SO4, and we're going to do an action line to get over to our grams of water to find our theoretical yield. So we got grams of H2SO4. I feel like I'm going to run out of room. 1 mole of H2SO4. This is stuff that you should know how to do. And this is our mole-to-mole ratio. Moles of H2SO4 to moles of water. And so I got 6 moles of water for every 3 moles of H2SO4 from my balanced equation. And for every 1 mole of H2SO4, H2O, sorry, I've switched over, is 18.02 grams of H2O from the periodic table. I'm going to calculate H2SO4 right now, and that is 98.09 grams. So now I'm going to get my grams of H2O when I calculate this out, which I'll do now. And in the correct number of sig figs, I got 11.0 grams of H2SO4. This is my theoretical yield. Thank you. It is my theoretical yield. That's how much I should get if everything went correct. So now, to find actual yield, I do my, to find percent yield, remember percent yield equals actual over theoretical times 100. My actual yield was given to me in the problem in this case, and that is 10.6 grams. My theoretical yield was 11.0 grams, so I times 100, and 10.6 divided by 11 times 100 gives me 96.36. Usually with percent you can add one more sig fig on there. These are each 3 sig figs, but I'm going to add one more. 96.36% yield, and that is pretty good. Okay, this is a little bit different type of percent yield problem, but don't let the big words mess you up here. Just let's work through it all together here. It says coal gasification is a process that converts coal into methane gas. If this reaction has a percentage yield of 85%, now that's giving you something right there when it says 85%, it wants to know what mass of methane can be obtained when you start with 1,250 grams of carbon and sufficient water is available. So let's see what we're given here. First of all, we're given a percent yield already. We know the formula for percent yield is this. Percent yield equals actual over theoretical times 100. And so the percent yield in this problem is 85.00%. What we don't know yet is we don't know the actual yield, which is what the problem is asking us to solve for, what mass of methane can be obtained. So this is what we're walking out of the lab with. And we don't even know the theoretical yield of methane, because this is methane right here. And it says we start with 1,250 grams of carbon. And it says how much methane can we walk out of there with. So we have to find the theoretical yield first of all. Once we do that, we can plug it into this formula to find the actual yield. So let's find the theoretical yield right now. So we start out with an action line of 1,250 grams, that's what we're starting with, of carbon. And then we're going to change that carbon, grams of carbon, to moles of carbon because we want to get to a mole-to-mole ratio. This is 12.01 from the periodic table, and that's 1 mole of carbon. Make sure you're writing those on there. And then moles of carbon down here to moles of, now this is where we switch over to our methane, CH4. And this is our mole-to-mole ratio. So we have 2 moles of carbon and 1 mole of CH4 from our balanced equation, and the coefficients on there. Then we go to moles of CH4, and then to grams of CH4. This is going to give us our theoretical yield of methane. For 1 mole, this is going to be 16.05 grams of methane. And so we're going to plug this in and get our answer. And the answer I got was 835.2414654. I'm not going to put this in scientific notation because it's not really our answer yet, but it is 835 grams of CH4. That's a 4. And that is this is what I like to do each time. I like to label that as the theoretical yield. I'm doing that for myself. You can just put TY if you need to. Theoretically, we should walk out with that much. But it says we only get 85% of that. Up here in the problem, it says 85% yield is what we're going to get. So what we need to do is we need to plug that theoretical yield into our equation down here. And so we're going to solve for the actual yield. Theoretical yield was 835 grams. And then this is times 100. Now in order to solve for this, we need to get that A all by itself. And so to do that, we're going to multiply both sides by 835. 835 here and 835 here. That's going to cancel those out, grams. And I'm going to divide both sides by 100 to get that. Whoops, that's the 1,000. I want 100. Divided by 100. And these cancel out right there. And so I get my actual yield is 709.75, which in the correct number of sig figs would be 710, and then in correct scientific notation would be 7.10 times 10 to the second grams of CH4 is what I walk out of there with. So remember, one more time, this is theoretically what you should get. But it says you only get 85%, and some reactions do that. Some reactions will only give you a certain percentage because you lose it to other things in the process. So if I wanted to make 710 grams of methane, I would start with 1,250 grams of carbon and have sufficient water. All right, here's one for you to try. This is just like the last one that we did. I've given you already the balanced equation right up here. And this is PCl5, and this is PCl3. Sorry, I couldn't do the subscripts on there. But notice what you're given. You're given a percent yield again. You want to know what mass of PCl5 is expected. You want to know the actual yield of PCl5. And this is what you're starting with, 73.7 grams of PCl3 in excess chlorine, which means that chlorine is our excess reactant. PCl3 is what determines the amount of product. So go through those steps, and I'll give you the answer here also. The answer is 93.2 grams of PCl5. Make sure you're going back and checking it out. Don't just say you're lost. Go back and check out the last problem. See how we did it. It's the same kind of process. So go ahead and pause it and do that right now. And finally, this is like our first problem that we did for our example. You are given a starting mass of hydrogen, in this case 79.6 grams of hydrogen, and it says you have excess nitrogen, which means the hydrogen is our limiting reactant, so we start our reaction line with that. To produce this much ammonia, 349 grams of ammonia, that's the NH3. This, if we actually produced it, that is going to be our actual yield. So we need to change this over to grams of ammonia, then do our actual over theoretical times 100 for percent yield, and your answer that you should get is 77.90. That's got an extra sig fig in it, so 77.90% yield on that one. Good luck. Don't give up. You got to do these. You can work your way through it. If you don't know how to do it, then go back and check out your notes or check out those other examples. These follow right along with them. All right, have a good day.